Hey everyone, and welcome. When you think about orthodontics, you probably picture braces, brackets, and wires. But behind all that metal, there's this world of super sophisticated biomechanical engineering. Seriously, it's a deep dive into forces, moments, and couples, all designed to solve a complex physics problem right inside your mouth. Today, we're going to pull back that curtain and look at the invisible engineering that creates a perfect smile. Let's get into it.
All right, so here's our game plan for today. We're going to start with a fundamental engineering challenge. What's the actual problem we're trying to solve? Then we'll explore the two major force systems orthodontists use, the super predictable one-couple systems and the really powerful two-couple systems. After that, we'll see how these big ideas actually translate into clinical strategies. And finally, we'll wrap it all up with the key takeaways on the biomechanics of a perfect smile.
So what is the core problem here? At first glance, it seems so simple, right? Just push a tooth where you want it to go. But nope, it is way, way more complicated than that.
And that brings us to the central question of this entire explainer. When you push on the crown of a tooth, the part you can actually see, how on earth do you get the root, which is buried deep down in the bone, to come along for the ride in a controlled way? How do you get that perfect straight line movement instead of just tipping the tooth over? Well, the answer starts with understanding one single, absolutely crucial concept.
And that concept is the center of resistance. The easiest way to think about it is like the tooth's center of gravity, or its natural pivot point. It's hiding about halfway down the root. So anytime you apply a force to the crown, which is way above this point, you're naturally going to create this twisting force, what engineers call a moment, that makes the tooth want to tip. So really, the entire science of orthodontics is about perfectly managing all the forces and twists acting around this one invisible spot.
Okay, so to tackle this whole tipping problem, orthodontists use two fundamentally different kinds of force systems. And knowing which one you're dealing with, well, that's the key to everything. It determines whether you can predict what's going to happen or if you're just estimating.
And this slide just lays it all out. On one side, you have what are called statically determinate systems. Think of this as pure, predictable physics. Every single force, every single moment, it can all be calculated with precision. You know exactly what you're getting. But on the other side, you've got statically indeterminate systems, and these are just so complex that you can't possibly calculate everything precisely. You can only get approximations. It's really the difference between a known quantity and a powerful but much less predictable beast.
All right, let's kick things off with the predictable ones. These are called one-couple systems, and their superpower is crystal clear control.
So, what exactly is a one-couple system? Honestly, it's all in the clever setup. You take a wire and you fully engage it in a bracket or a tube at one end. That part creates what's known as a couple, which is just a force that creates pure rotation. But here's the trick. At the other end of the wire, it's tied with just a single point of contact. That simple move is what makes the whole system statically determinate. It just simplifies all the physics, takes out the guesswork, and lets the orthodontist know exactly what forces they're working with. And check this out. This is a perfect example of how it works in the real world. This is an intrusion arch, and it's designed to push the front teeth up. A wire is locked into the molar tube in the back, then it extends forward and gets tied to the front teeth. Now, the beauty of this is if you apply, say, 40 grams of force to push those front teeth up, you know for a fact that the molars are feeling an equal and opposite 40 grams of force pulling them down. You also know the exact tipping forces on both ends. Every action has a known, predictable reaction. No guesswork at all. Okay, so that's the world of precision. But now, let's jump into the more common but way more complex world of two-couple systems. This is what you're probably picturing when you think of braces, that continuous wire running through all the brackets. The second you take that same wire and lock it into a bracket at the other end, bam, everything changes. You've just created a two-couple system, and the physics instantly becomes statically indeterminate. The system is now incredibly powerful, but trying to calculate the exact forces and moments, yeah, good luck. It's pretty much impossible. And this is where it gets absolutely wild. You'd think you'd need big, obvious adjustments to get big results, right? Nope. In these complex systems, a tiny bend in the wire, one that you could barely even see, can unleash forces that are just orders of magnitude larger than you would ever expect. Okay, just look at these numbers. This is kind of mind-blowing. You take a standard 16 mil steel wire, right? And between two brackets that are just 7 millimeters apart, you put a little step bend in it that's only 0.35 millimeters high. We're talking about less than the thickness of 4 sheets of paper, and the vertical force it generates from that tiny bend, a staggering 347 grams. So 347 grams. Why is that number so important? Because in the world of orthodontics, that is a massive amount of force. It's way, way too heavy for a delicate movement like intrusion, trying to gently push a tooth up into the bone. So this heavy force just overwhelms everything, and you get the exact opposite of what you want. Instead of intrusion, you get extrusion. The tooth gets pulled down, not pushed up. And this quote from the source material just nails it. It's these unexpectedly huge forces from what seem like tiny little bends that explain this really common clinical outcome. It's not a mistake. It's just the raw inherent physics of a two-couple system doing its thing. You just have to respect that power. All right, so we've got these two different force systems in our heads now, right? The precise one and the powerful one. Let's see how they actually show up in the clinic. Like, what are the two major strategies that orthodontists actually use every day? And this slide lays it all out so clearly. On one side, you've got segmented arch mechanics. This is basically the divide and conquer strategy. You use those super predictable one-couple systems to move just specific teeth or groups of teeth with total control. But on the other hand, you have continuous arch mechanics. This is the one-wire-does-it-all approach. You run a single wire through all the brackets, creating those powerful but complex two-couple systems. It's not as precise for sure, but man is it often more efficient for getting the whole arch aligned. Okay, we have gone through a lot of physics here. So let's pull it all back together and really make sure we lock in the big ideas from all this. So what's the bottom line? First, control is key. Every single thing an orthodontist does is about managing that natural tendency for a tooth to rotate around its center of resistance. Second, there are two systems for the job. You've got one-couple systems for precision, where all the forces are known. And you've got two-couple systems for power, which create huge forces from tiny bends but are hard to calculate. And finally, strategy defines the mechanics. The choice to use a segmented approach or a continuous wire isn't random. It's a fundamental choice between these two core principles, precision versus power. And all of this leaves us with a really cool question to think about for the future. We've seen this trade-off, right, between predictable determinate systems and powerful indeterminate ones. But with all the amazing tech coming online, like 3D printing and AI, could we be heading toward a future where orthodontists can design appliances that are perfectly determinate for every single unique patient? I mean, imagine that. Ultimate precision, totally customized. It's an exciting thought about where this invisible engineering is headed next. Thanks for watching.